Hello, everyone. This is my honor to introduce the speaker today, Dr. Weisen Shen. Weisen Shen earned his bachelor degree from University of Science and Technology of China, USTC, in 2008, and got his PhD degree from CU Boulder in 2014, and then he worked as a postdoc in the University of Washington University in St. Louis, and before he joined the Stony Brook University, and now he is an associate professor in the Department of the Geosciences at the Stony Brook University. And Dr. Weisen Shen is a seismologist and specializing in the seismic imaging. And he always trying to, understand the structure of the Earth's interior. And his research is driven by the two significant questions. And the first is, how can we improve the accuracy? And how can we improve the reliability of the seismic imaging? And the second is, how can we use the seismic model to provide more insights about the composition and the temperature and the tectonic evolution of the Earth. And let's welcome Weisen and for his.
Thank you. Thanks. I'm very honored to be here, actually. I love Austin a lot because 15 years ago I was here in town. There was an Earth School meeting, and I was a young graduate student. I was so impressed by the smoked brisket they offered me. Do I still remember the talks in that workshop? I don't know, but I just love the town. And so when Chuanming and Duncan invited me a few months ago, it was a no-brainer. I have to come at this time. So before I came, I was debating with myself, what should I talk about? Should I talk about our trip to Antarctica, show you a bunch of pictures and videos? It's cool, right? But it's cool to my 6-year-old. In front of this group, I think it's better to take the opportunity to talk about the rocks and across the tectonics geology. And I will learn a lot of insights from this audience than just showing the pictures. So I brainstormed with myself. I came up with a plan when I was in the field. I even list how much time I should talk about each individual things. I will see how much I can follow this timeline. But overall, I'm going to present you a talk with a very traditional structure. I will first lay out the ground and why I study this, why there is any, why do I ever spend any time on that? And then I'm going to talk about the so-called status quo, the traditional way to do business, and then report to you with some progress in the technical side, and follow that with the more provocative things that we are trying to do, and end this talk with a summary and outlook. I will try to make it within 15 minutes, but I know I have way more slides for that. But I still welcome you to ask any question if you come up with during my talk. Okay, so first thing, why do I ever do this? If you ask any structural seismologist, why would you ever care about the crustal structure? They will come up with those words, fancy words, saying this is important because those fancy words are important. But instead, I'm going to show you some examples that I recently find very fascinating how structural seismology is contributing. This is one example, a recent paper published by some of my colleagues talking about how mammals, the animals that live in the Western United States, how they diversify their species over time. And what they found quite interesting. You have a very diverse mammal group, not because it's the landscaping is diverse itself, but because they found it's diverse because of the changing of the landscape over time. Quite interesting, quite new to me. But if I read that paper very carefully, I realize they are doing something actually geophysics. what they were trying to do is they try to correlate the mammalian diversity with the geodynamic modeling. And if you drill into the details of the geodynamic modeling, they have to use the models of topography over time. And in order to do that, if you look more into the details, they have to start somewhere in the modern days. So they have to use some model, Earth model, to start with. And the Earth model they use happens to be the model that we published about 10 years ago, right? So that was, wow, when I was doing this work, how do I know someone who is studying mammalian diversity is going to use my seismic model to get that correlation? That's definitely was not part of my plan when I was doing this work. Although I have to admit, when I was pursuing this work, I have spent a lot of effort into constraining the uncertainties, the errors. We developed this technique, try to map out the crust thickness, but also associate with it every way we can do to the uncertainty. This is the random uncertainty, about 2 or 3 kilometers for Western US, where the ecology community is concerning. And we also did spend a lot of time working on the errors, systematic errors, and we found maybe it's not that big, 1.2, 1.5 kilometers of errors of not considering the crust like VPVS ratio, things like that. So if they want to use this seismic model, by count the topography change, 2 or 3 kilometers of crust thickness in error will perhaps corresponding to 500 meters of topography, right? Using isostasy. Not that big. It's perhaps okay, an animal can live in here, another 500 meters of elevation gain. They can live there as well. But what if my crust model was wrong? Beyond that, when I was producing this model, I was very confident, a naive young guy, very proud of this work. What if my crust model is not that great? This is something I'm going to discuss. And if that's the case, those scientists, they are perhaps in trouble. They have to redo their work. And we'll see. There's a second reason I recently also find fascinating about structural geophysics is that I spent time in Antarctica. And the reason why we study that place is because of ice sheet. And it turns out one physical quantity, the geothermal flux, is quite important to model what's going on in the ice sheet. This is one of the review papers specifically calling out the importance of this quantity. And you can imagine there are a lot of different ways to change this quantity or to influence this quantity, right? You have the heat coming out from the mantle, you have the heat producing elements within the crust, you have topography, hydrocirculation. What can change that? One thing I'm going to touch base today will be the heat producing elements in the continental crust, then how they change our understanding to the geothermal heat flux. Here is one example. We know geothermal heat flux is not well constrained in Antarctica, but how badly it was constrained. Here is one example. On the figure here is 2 maps from a very similar technique. They are both derived from Curie depths. Look at how big change in West Antarctica. This is one place you have high geothermal heat flux, more than 150 milliwatts per meter square. In another map is the opposite, less than 100, less than 80, from very similar technique, right? They are both magnetic, both Curie depths. And if you drive into the details, you realize there's a lot of things that we do not know. For example, in order to get the geothermal heat flux at the surface, you have to assume something if you only know the Curie depths. Curie depths is the depth to the temperature of 580 degrees C. Assuming like there is a steady state, there's no lateral variation of properties at a continental scale. How come? Right? It has to go with this exponential distribution with depths. Are we really confirming that? If you think about how the heat producing elements is changing, right? This is one of this is the heat-producing elements here. It's changing. It's huge. It's a horizontal variation of the heat-producing elements. This is one of the maps I'm going to discuss later in this talk. It can be an order difference from places to places, just because the crust composition is different. But even the papers published 5 years ago, we are still making those assumptions. Then we know it's not true. And then about the continental scale, if you drill into the regional and the local scale, there's another paper by Jordan et al. Published in 2018. They are looking into, some of our colleagues are very familiar with the radar on the ice, and try to say something about how much geothermal heat flux will produce the melt, sub-ice melt. They concluded that in a place where it's very tectonically stable, you get 120 milliwatts per meter square. That's 3 times of what you would expect. And they say, maybe that has some question mark, but we have geological evidence. What's the geological evidence? They found 1 out of 17 basement rock sample, not collected locally, but collected down the stream. Then it has one value that's about 83, and then they conclude, maybe that can give us some geological support. 1 out of 17 to talk about the region. And if you pin down that particular rock sample, that has a heat-producing elements about 80. That, if you look at how this number correlates with the overall crust rock collection, it is corresponding to some rock that is super felsic. Do we know that the place has a super felsic crust? We don't know. It's covered by 2 kilometers of ice, right? So just using the remote sensing way to pin down this value is very, very difficult, even we know it's critical. But this also teaches us, in order to confirm this or disconfirm this, we need to know more about the geology, more about the crust composition. So today what I'm going to go through with you is knowing the importance. We are going to make some contributions to this. It's already 15 minutes. I was planning to talk about it by 5. We'll see how it goes. Okay, now let's move into the next part, the status quo. Okay. First, I'm going to review how seismologists, especially the traditional structural seismologists, are doing this work. And this work I'm going to present to you is from a graduate student, Han Xiao Wu's recent work. I'm lucky enough to work with a group of students in my team. It's a combination of graduate students and postdoc. But the next 15 minutes, I'm going to mostly focus on the Ms. Wu's work. Okay, so let's examine the status quo. One big thing in the status quo of the composition, structural seismology is Hiro Kanamori. I shouldn't call it the status quo. He's a great scientist and has done great work. And one of the greatest work is in his top 5 citing list. It is still widely used these days. Is a simple, elegant, very easy to use way to map out the crustal thickness. Okay, this paper was published earlier, just talking about California. What does this method do? Basically, what it's trying to do is to use individual earthquake recorded at a single station. If you examine the body wave, it records from teleseismism. And you can constrain both the thickness and the VPVS ratio. Very simple. What does it try to do is, whenever you get an earthquake, the Earth's seismic wave will bounce near the Moho. And once you look at it, it's bouncing around, you can find the different waves arriving at a different time. And if the model is good in certain perspective, like the thickness is good, or the VPVS ratio is good, you can stack those energy from different events. And where the energy is maximized is where your parameter is correct to the real Earth, more or less. So in this case, it's a very nice, simple method. You have a seismometer out there for 2 years. You can collect those events, do the stacking. You get the Moho depths and the VPVS ratio, the ratio between P velocity and shear velocity. And this method has been widely used, as I showed you. It is still cited more than 100 times per year after 25 years. And there has been some development. For example, you can, in addition to looking at the Moho signal, you can also look at the signal from the bottom sediments. So you can do, if you happen to have also sediment signal, you can map out both layers, both their VPVS ratio and crust thickness. Does it have any drawbacks? It does. Actually, the authors are quite honest about what they are doing. So they for example, they say that we can map out the crust Moho depth and VPVS ratio, but we have to make assumption about the absolute velocity. And it turns out, given the sensitivity of the different waves, they believe the dependence of crust thickness on VP is not as strong as on VS. So if you make a reasonable guess about the crust VS, you can perhaps get the, I'm sorry, on the VP, you can get the Moho depth and the VPVS ratio right. Do we already know that? I'm going to come back later. The second status quo, or widely used method, is the surface wave. I happen to work with a great surface wave scientist, Michael, on one of the techniques. So basically, okay, this is another well-cited paper. Again, this is actually on the upward trend. People are using that more and more often these days as a standard data processing technique to process broadband seismic data. What they were trying to do is, if you take the ambient noise recorded by seismometer, you do the cross correlation, you can bank out the surface wave traveling between the two stations. And this wave happened to be period dependent. And longer period arrives earlier, shorter period arrives later. Once you have that information, this is corresponding to deeper structure. Shorter period is corresponding to shallower structure. Then you can say something about the depth-dependent structure of the Earth, right? And this is a big promotion because traditionally people can get only surface wave from seismic data, earthquake data. And then the data is concentrating on the relatively long period side. You can get some mantle, uppermost mantle structure. Crust structure is less high, the resolution will be lower. For example, this is 20 seconds radio wave. You can see the great big scale basins, but the details are not in the signal. And the beautiful part of ambient noise is that ambient noise spectrum is on the lower end, shorter period end. You suddenly gain the resolution to the shallow structure. And this was my PhD work. I joined his group, look into the ambient noise, do the measurements across the United States. This is the US survey, initiated around 2004. Oh, now I remember, 15 years ago, I came here. It was our scope workshop talking about this array in Texas. So I was using this array, looking into how the surface wave travels from shorter period to longer period. If you just look at a shorter period, you already recognize a major basin in the United States. And then what I did is I combined this information together with some receiver function waveform. Then I get a model, depth-dependent shear velocity model from surface to greater depths, together with crust thickness with uncertainty assessment. I like this work. I was very proud of this work. This is exactly the work was cited by those geodynamicists and ecologists to study the mammal. But it has, again, has its problem. One problem is that I'm truncating the signal of this body wave signal just to use the first 10 seconds, because the later signal will be noisier and it's going to be distance dependent. It's less reliable for me at that time. So I have this problem. I don't get those reverberations. So I don't get to see the VPVS ratio of the crust. But it can affect my surface wave data. At that time, I did do a thorough error analysis. My conclusion is, if the VPVS ratio you assume is about 1.75, and if the real Earth goes from 1.7 to 1.8, it's not that a big problem. You can it affect you about 1.5 kilometers. Again, not a big deal if you study mammals and can live plus minus 500 meters. But VPVS ratio is actually a wild card here. Why? We later did do a synthetic test. We take a model, start with a model that we know, we call it a synthetic model, get the data, then we were doing the inversion for the 2016 model, and allow the crust VPVS ratio to vary. We get different models that can fit the data equally well. You can see 3 fittings in the picture on the left, and they are corresponding to 3 different models here. Their Moho depths can differ up to 5 kilometers. And this is huge because if you look at the crust VPVS ratio variation in the United States, it actually goes from 1.6 something to 1.95. And that will be corresponding to a huge change VPVS ratio of lower end and a lower end 1.62 and 1.8 is corresponding to up to 10 kilometers of Moho depth difference. Right? If I was one of the co-authors in that mammals diversity paper, and I know the seismic model I was using have up to 5 or even more uncertainty, I would definitely worry a lot. And I have to blame the seismologist. Why is they doing a lousy job? Okay, we're trying to save my ass. This is what we are trying to do, okay. Now it's the third part. Oh, we are 25 minutes there, okay. We are doing, what's gonna happen is now, let's look at the same example. If I look at this traditional method that we employed about 10 years ago, we are definitely inverting for the surface wave data, the reserve function waveform for the first 10 seconds. And we conclude that all the misfit is small enough that we deem them to fit the data. But we cannot distinguish 3 different models with different VPVS ratio. But if you go back and look at the classic 2000 Calamari paper, if we can employ this piece of data, looking at the stacked energy from all those possible different models, their stacked energy is quite different for the 3 different models. There is one area that has particularly high stacked energy because it's corresponding to the correct VPVS ratio, because those later signals are sensitive to that value. So what we did is simple. We take the 2 classic methodologies, velocity still, we just combine them in one method. When we are doing a Monte Carlo machine, we maximize the H-cup energy and minimize the misfit at the same time. Okay? So it's just one little change. Incorporating this, where the traditional model cannot distinguish them. All those blue dots in the model space, we cannot distinguish with the traditional method. Suddenly, we find the energy is close to where the true model is. And this is from a synthetic test. So if our Monte Carlo machine allows us to just pick those models, right? This is the result from the Monte Carlo running. It's a subset of those models. Suddenly we solve this crust VPVS ratio, Moho depth, and deep crust VS trade-off at the same time. It's like a one-stop shopping to get all the parameters done. Traditionally, if you go out, put out a 30 seismic sensor, you have to support 2 PIs with 2 individual students. One does do reserve function, one does do surface wave, maybe a third postdoc to joint analysis. Now you don't. You just need 1 person using this method and get it solved. Look at the posterior distribution. This is for the VPVS ratio. With the new inversion, suddenly we can constrain it. And as a result, Moho depth uncertainty goes down a lot. And this is from the synthetic test. If we add noise, it's still working. If we apply to real data, it's still working. So we expanded to about 450 stations in the northwestern US. And it's great. We get a new model with reduced uncertainty. And suddenly the crustal Moho depth uncertainty is the middle panel on the right side. Get reduced to less than 1 kilometers. Once you consider, even when we vary all the possible VPVS ratio, we release and constrain, we get it better. This is like pick the best thing of the two traditional methods. And we suddenly solve this problem, which means we now get better crust thickness. And perhaps those ecologists, if they rerun their model, they will get a better understanding. They can double confirm or revise their conclusion now. Okay. That's the technical progress part. This work has been published last year, and we'll see how our community feels then, right? You suddenly don't need that many students to process your data. Yeah. Okay. The next part will be more dangerous for me to talk about. I call it provocation because it was hard for me to push the next part out. We have a technical progress that allows us to constrain the Moho depth better, shear velocity better, or even VPVS ratio better. Can we say something about this? And the work was done by Siyuan Sui. He was my graduate student. He now has left Stony Brook. But all the next 20 slides is all the work that I have done with him. Can we say something? Now let's take a look at how people used to say something about the crustal interpretation of the seismic imaging. A geologist has a long time using p velocity to interpret the signal and say something about the deep crustal composition or rock types. You don't use shear velocity. Number one, you do not have good shear velocity, right? You go out, do a deep seismic sounding, what you get is p velocity. And the shear velocity ambient noise is more recent. So we are used to p. But if you look at S is not a very good indicator either. Because this is a plot. Here is the individual crust rock samples measured in the lab to get the silica content. This is a major oxide that you use to do the first order categorization of your crustal rock, right? If a rock is felsic or mafic, determined by the silica content. Plotted horizontally with shear velocity, color-coded by the VPVS ratio. If you know a VPVS ratio of the crustal rock, in the past, the seismologists will say, oh, maybe we can say something about the quartz content because quartz has a particular low VPVS ratio. But if you look at those rocks, the same VPVS ratio, like the lower value, 1.7 to 1.75, their silica content actually can vary from the mafic end to felsic end. It's actually not the case. We can say something about composition. If you look at the shear velocity, the same. I cannot use the S word. I'm sorry. When I was in the field, I was so used to. You cannot use that quantity to constrain the composition either, because the same low shear velocity can be corresponding to rock types with different composition. The same thing for VP. So Brad Hacker has this famous paper back in 2015, 10 years ago, saying, oh, seismologists, you have no business here. Maybe I'm exaggerating that, but it is dangerous. If we get a seismic work and directly say something about the composition, we just cannot. But if you rearrange the database, you just don't plot it like this, but plot it along shear velocity and VPVS ratio side. What do we see here? It's exactly the same data. And the silica content is felsic rock. They actually concentrated more on one corner. mafic rock on the other corner. There's a trend that we can observe here, right? And you may say, okay, this is a crust rock you collected and do the labs. The lab measurements have uncertainty. Let's look at the thermodynamic results. You can calculate the phase equilibrium and the deep crust condition. Look at the mineral assemblage, calculate the velocity. It is the same trend. Well, the trend is slightly different from what you see from the lab. There's a DC shift here. But it's generally the same trend. So if we can capitalize with this trend, then that will be a big step forward. Well, in order to do this, you need to know the shear velocity. I thought I knew that because I published this 2016 paper. I didn't know the big uncertainty at that time. And I have a student working on the VPVS ratio. We were looking at the automatic VPVS ratio just using the classic Calamari 2000 technique. It was quite noisy. And we spent tons of time to reprocess the data, do the quality control, employ the two-layer methodology. Now we get a more reasonable map. Then I realized, with this knowledge and the trend, maybe we can do something. And what we did is very, very simple. You cannot imagine how simple it was. What we did is we take any of the shear velocity model for every station, depth dependent, correct for their temperature variation, assuming some initial temperature model. What's left is the variation might coming up from the composition. Take the VPVS ratio, and at that time we only have one value for the whole crust. So we assume it doesn't really change over depth. Actually, it changes, but this is a big assumption. And every depth, I have the shear velocity, I have a VPVS ratio. I just go back to this map and pin down the composition for this corresponding shear velocity and corresponding VPVS ratio. What I end up with is a silica content profile. Well, all of the seismic property have uncertainty, so the silica content also have its own range, possible range. But if their velocity, seismic properties are different enough, their crustal composition profile, they are actually well separated. And if you integrate them, you get an average crustal composition. They are also well separated. We may assuming this is constant. You do not have to. You can actually change it so it varies with depth as long as the average is the same as estimate. But once you do that, you change the shape of this a little bit. Bulk silica content distribution stays relatively unchanged. It's a very stable estimate for the bulk crustal composition. So we just go ahead and use our US model and produce this map. Bulk crustal average silica content rate percentage across the United States from the US array. Definitely I strip out the sediments. I'm only looking at the basement and below. This is a crazy map, a lot of dots, but there's some trend here, which is quite interesting, right? Western United States is different from the Archean core, and it is also different from the eastern coast. Okay, I was skeptical at the beginning, and then I look more into the details. Okay, whenever you have a three-dimensional model, now you can look at the slice, look at different depths, look at how big uncertainty they are, look at how they vary horizontally, look at how they change from tectonic province to another tectonic province. You can do all sorts of things. They can all be bullshit unless you pin down with local geology. So that's the first thing we try is we look at the variation in the Western United States. It has big enough variations, and we can look into things like what's the volcanic rock type. If I plot the location of the mafic volcanic rock samples collected, individual blue dots that corresponding to where I find the mafic crust, which is plotted as blue color here. Low silica content crust has the mafic volcanic rocks. Maybe it says something. Another direct example. Some people, some geologists, they can collect this so-called xenonese brought up by the volcanoes of magma from the deep crust. They can analyze their chemical composition. They can do the thermal barometry to look at the temperature and the pressure, so to infer their original depths. We can compare that. There are 3 different sites in northern Montana. I plotted their silica content versus depths we infer from thermal barometry, together with the seismologically constrained silica content profile. It's not that bad, right? So which means, maybe I don't need to collect the samples. I can still say something about the crust composition with a certain confidence. And we did the same thing, so we can compare our composition with granulite facies xenonese, right? They are very consistent with each other. Not bad. So looks like this model, simply generated, as long as you have good enough shear velocity and VP-base ratio, is saying something. Not everything in this model is bullshit, but that's still a big step in interpretation for structural seismologists. Suddenly, I don't know what I'm doing. Maybe I'm empowering our communities to say more about the geology, but that can also be dangerous, right? We can say something that we don't know. And one more step forward, if we say something about silica content, the bulk geochemistry of the crustal rocks is telling you something with potassium, thorium, and uranium, because they all somehow correlated with silica content. Generally, when you have felsic rock, you get more heat generation. You can use that trend, convert your silica content to heat generation. And once we have this, we suddenly have a depth-dependent heat generation model that also varies horizontally. We do not have to assume everything is the same on the continental scale. If you combine this method together with surface temperature, surface heat conductivity, in the US, you can measure surface heat flux. You can get a Moho temperature from maybe PN tomography. You get the Curie depth from geomagnetic studies. You can suddenly turn all of the constraints into a 3-dimensional conductive thermal model that can fit all of those data. So last year, we did do this work. We convert all the data we can find, including the newly generated heat production model. And we built this 3-dimensional thermal model. And here is the interesting part. We built this model. We are very happy. We compare with the USGS national model, very similar, because we are using very similar data. But we have one big constraint, which is heat generation. So there are certain places we improve that model. But more importantly, we did do this test. If I remove my surface heat flux, I only use the surface temperature, Moho temperature, heat generation at different depths, as well as Curie depths. Can I back out my surface heat flux? I use isostatic data. If I use all 4 thermal parameters, including the heat generation, I have this blue distribution that is centered where I know it is true geothermal heat flux. But if I remove the geothermal heat flux, the other 3 data can still constrain this geothermal heat flux reasonably well. This means if you know this in your place, then you cannot measure geothermal heat flux. It can give you the constraints to a certain degree, including considering the horizontal variation in in heat-producing elements. So this might have a big implication for Antarctica, because suddenly we find a roadmap that can help the community start from seismic structure, constrain the crustal composition, constrain the heat generation, and then you can build a crustal thermal model and predict the geothermal heat effects. And they are all internally consistent. You don't worry about it. Well, this model fits one data, but it doesn't fit another one. And then I believe is the way we can go move forward. And well, I call it a provocation because when we just came out of constraining the chemical composition, we try to say a lot about how the continental crust evolves or got generated. We are going in an uncharted region with my seismic implications. We'll see how that goes. In the next 10 years, we'll see how people see this work. We begin to see some other seismologists begin to follow up this simple method, but whether the geologist community will buy this, either it's jam or shit or jam in the shit, we don't know. We'll see. Okay, next part I want to talk about what's a way to move forward. In terms of summary, very simple conclusion. If you combine all data, all traditional methods, they're all good. If you have a geophysical array like the US array, that's wonderful, right? It enables us to do the continental scale imaging, say a lot of things about sediments, about the crust composition, about the crust thermal structure. And we can apply it to polar regions where thermal boundary condition is definitely needed, eagerly needed to predict the behavior of the ice sheet. But if we believe those places are where we want to go move forward, we need this array like this to be deployed in Antarctica and Greenland. We were doing a little bit of work. Last year and the season before, we went to South Pole, put out 9 to 10 broadband stations. Those are stations similar to the US array. And also hundreds of the nodes, we begin to densify the observation in Antarctica. We were using this so-called wheeled truck platform. Very, very revolutionary for us to manage the logistics there. This number of array, in the past, you cannot imagine that you can do that within a season. Now it's possible. And they are bringing a lot of data back to us. They can record seismic events like broadband. Those are the smaller nodes, very cheap, easy to deploy. They can record noise from the South Pole station. This is an interesting plot. We always think the QSPA, the broadband station near South Pole, is the most quiet station in the world. Turns out it's not as quiet as we thought. There is a noise that you can see that decays when you go further away from the South Pole. The noise is from the activities of the station, right? And it's a bimodal noise. There's a daytime, there's a nighttime. It's quite fascinating. And also, if you really want to build the most quietest station, you have to go at least 100 kilometers from the pole to do that. And we are still in the middle of just getting the data a month ago. I just came back in January, and we have some initial result. Maybe I can report to you in the future. I think this is my last slide. I'm 45 minutes on time. And thank you very much for sharing your time with me.
So questions for Weisen? We don't have the UTIG Cuba Doom, so I'll run the microphone to anybody who's has a question. Harm.
Great talk, Weisen. I'd like to first ask a more less technical question. You had an uncertainty in your receiver function. Receiver functions, of course, come with some uncertainty.
Yes.
I was surprised that there was not a stronger correlation between, for example, the tectonic setting and the uncertainty, what you call the a posteriori uncertainty of your receiver functions.
Posterior uncertainty,
so
yes.
Is it purely a function of the data, or since the receiver function method is somewhat flawed,
yes.
Doesn't it also depend a little bit on the nature of the Moho?
Yes.
The Moho
yes.
can be influenced by magmatic, metamorphic,
yes.
or tectonic processes. So I was surprised to see not a stronger correlation with a spatial correlation.
There is some, yeah, you're right. First, it's noisy, right? But we can say something, a big pattern here, large scale pattern. There is places like, this is a standard deviation of the Moho. And this is mostly coming from the receiver function, in fact. And you will find that in places like basin range, where the receiver function is quite sharp, signal is quite clear because Moho is sharp, uncertainty is smaller on the blue side. If you come to a Green River Basin or Williston Basin, you generally have more reddish color. We are actually constraining the Moho worse in the past. This is a 2016 paper. The new methodology, we believe we can constrain it better partially because we begin to use the multiples in the signal. There's one example here. I think one station we did look, I show here is this one. For example, this is one station in the north edge of Denver Basin. If we use the 2016 method, we do have a band constraints to the Moho depths. But once we separate out the sediment signal and we incorporate with the multiples just from Moho because they come much later, we can actually constrain this station on a relatively good sense. The Moho becomes, from the new work, becomes more, as you said, more homogeneously well constrained, except a few stations in a Green River Basin.
Great talk. So I have a question.
Do you want to use that?
Okay. Seems that it's on, right? Okay. So I'm curious about the heterogeneity in your result observed regarding the Moho depth, because it should somewhat be associated with the topography, right?
Yes.
If you're assuming an isostasy.
Right.
Have you compare it with the topography of the Western US, and have you been able to confirm that the heterogeneities are true?
That's a great question, because a lot of my colleagues, once they get a seismic model to the first order, the first thing is to compare it with isostasy. The frank answer is we have not done that work. It was not our intention to do the geodynamics implication right away. The first thing is to make sure our data was fit. But we do see some interesting signal. For example, if you look at the northern basin range, in our previous generation model, we already see a thinner Moho, although the topography is about 1 to 2 kilometers already. But the new model is even thinner. If we are supporting the same topography with a thinner crust, even thinner crust, there's an implication in the mantle dynamics there. Something can be said in that place. The paper is still new. We have not spent time on that. But I think that's one of the directions the structural seismologists, if they decide to employ this method to a greater region, we have to revisit this problem. There were papers by Fan-Chi and Brandon Schmidt talking about the topography versus the isostasy. I think that's another work we have to come up with. Yeah, thank you.
Any student questions? Any other questions?
A simple question that comes naturally from the last one too is that what about the gravity field? I mean, does it make sense?
Yes,
to use gravity as a constraint?
yes. That's actually in this paper we did compare with the gravity observation. One reason is that we find this edge of the west eastern basin range becomes sharper, and we compare with the gravity data, and it actually supports a sharper Moho variation in this place. And definitely in the long run is to compare the gravity on the map view instead of just along a profile. And if one can go even further beyond, we can incorporate the density into the inversion. That's another way to do this. I have been talking about that for the past 10 years. I've never done this. I'm a lazy person, and but then it can also be a great project.
Any other questions? Oh, yes.
Thank you. I really enjoyed your talk. I don't think a lot about the deep crust, but I think about what is at the bed of an ice sheet.
Yes.
And I was wondering how these sort of compositional variations relate to other changes in the mantle that vary throughout time. For example, in Greenland, there's been arguments about the passage of the Icelandic hotspot as being a driver in what we see today.
Yes.
Is that something that you resolve when you're assigning the changes
composition,
to
right.
composition, or
Yes.
is that a sort of separate?
Yes, that's a great question. So this is about in a place in Greenland, then you expect it to be a stable continent, but there are signs of a high geothermal heat flux, and people relate them to the past hotspot track. I think, again, this is one way we can pursue this is to go there, look at the seismic data and see if indeed there is any signature about the mafic intrusion from this possible hotspot track. If indeed it is strong enough to change your geothermal heat flux, it might have already changed your crust composition. Perhaps in two ways. Number one, if you see a felsic rock there, maybe you don't need a hotspot track to interpret your high geothermal heat flux, right? Because it naturally might have more heat-producing elements. But on the other side, if you do see a very mafic deep crust, it's perhaps saying something about the past tectonism. Currently, we are also developing a method trying to layerize our model. Now we only have one layer information about VPVS ratio. It's frustrating. In places like Southern California, you can use local earthquakes to have more say about the VPVS ratio changing within the crust. But now we only have one layer. We are trying to bring more data to make it more vertical resolution into the model. It's still ongoing work. We have some interesting results. If you're interested, we can talk more. But I think that's also another potential project to pursue. Yeah, I'm now disclosing all of my proposal writing ideas to all of you.
Well, I was going to say, I think it's a really good idea to have a seismic array, or you convinced me it's a good idea to have a seismic array like you had in the US for both Antarctica and Greenland.
Exactly.
So if I ever review that proposal,
Exactly.
I'll be watching for it.
We do need a community to pursue that. Yes, that's something I'm thinking of too. In the next decade or so, I think technically, logistically, we can begin to think about that.
Your geothermal gradient had a big anomaly in southern, I think, Arkansas or northern Louisiana.
Yes. Yes. Let me go there. A lot of things here in this map. Let me see. Okay. First, this is all observation. Okay. The geothermal flux, we also incorporate the data from the surface heat flux. The model is here. And this is the temperature and different depths. And where is my predicted geothermal heat flux? Let me see if it's, no, did I show it here? This is a resulting temperature model.
Moho temperature.
There's a Moho temperature here, right.
I just wondered if there's any, if you know what that comes from. Just that one particular spot in northern Louisiana.
Yes. Okay, how do I interpret this? I think mostly this comes from one piece of data. I believe it's from the Curie depths. It has a very shallow Curie depths. Why is that? I think it's something to do with the nature of the Curie depths. The Curie depths can be a temperature sensor, but it can also say something about if you have a very shallow Moho. That's where your rock stops to give you the magnetic signal. I think here there's a shallow Curie depth might rise from the thin crust that was not considered in the past of the interpretation of the Curie depths. But also we recognize there's also a higher surface heat flux. So our model ended up with incorporating both knowledge to give you a high temperature in that place. Geologically, why it is there, actually, frankly speaking, I don't know. Is really the surface heat flux coming from the real hotter crust, or is it simply a result of more complicated hydrocirculation in this place? I haven't dug into that area yet. We know some places like Southern Dakota is a big problem, the hydrocirculation. But so far, what the answer I can give you is its Curie depth and the higher geothermal heat flux, and is giving me high temperature in my resulting model.
So I have maybe a follow-up in this area. One of the assumptions that people often make is that the thermogenic production in the crust decays with depth.
Yes.
It actually occurs to me you can, in a way, attempt to test that
Yes.
on a
Yes.
continental scale.
Yes. Yes. And we do see that in our model, decay with depth. It's just not decay that beautifully, exponentially as the theory produces. And we do see that. And partially because our composition is getting more and more mafic with depth. And that's because our shear velocity generally increase with depth, even you consider the temperature variation.
But there is a potential then to go a step further and note that the curve, as you say, it's not perfectly exponential, but also based on the lithology, or based on the silica percent. If you want to do it that way, you could actually generate curves that would be better than just the exponential.
Exactly, yes. And I believe that curve should be regionally varied. And we can say something about that. Yes, indeed.
I think if this clock is right, we've got time for another couple of questions. But,
Thank you for a great talk. I enjoy it a lot. I only have a small question about something related to the reset function in Antarctica.
Yes.
As we know, there is a very sharp velocity, interface between the ice and the rock. And I wonder whether that will, introduce a lot of new signal in the reset function. And if it is, how you deal with it? Because you are caring about the, the crust.
Yes,
Yeah.
yes. The question is in Antarctica, you have a very thick ice layer, and then it's a low velocity layer. It's going to definitely generate a lot of reverberation in the reserve function, and we do see that. The good news is we tested the QSPA, the station at the South Pole. We find that those reverberation is mostly in the first 5 to 8 seconds. And the reverberation from Moho can still be somehow used. And if we weight up those signals, we can still get some sense of the crust thickness and the VPVS ratio. So the key part is we need a good ice model to make sure that we are predicting those ice reverberations. And, so we are not merging their energy into the later phase when we do the stacking. To me, the ice layer is just another sediment layer. Right? Ice is a mineral, and we know the depths, fortunately, than many basins. So we can predict where they are to some degree.
time for one last question. I might go ahead and ask a question. So, Earth scope for Antarctica. What's more important, the duration the stations are out, or the density of the stations, in your opinion?
Oh, this is a great question. Do I want to put, okay, if I have a logistic constraint, should I choose more station or choose longer deployment?
Yeah.
The true answer is I want both. And how do I do this? Okay, I'm not just saying I'm a ambitious people. I think the technology is there to allow a station to stay there a little bit longer. We just need to use rechargeable battery and a new design the power system. We need to capitalize the wind there, especially in high plateau. We need to send the data back without servicing it. Currently, we have to service it every year, and that's expensive. If we can solve that problem, a station can be deployed there, and for 3 to 5 years, you don't have to touch it. More stations, I think with the wheeled truck, I can do that if I can make the station smaller. Scientifically, if I still have to balance this trade-off, what should I do? I would like to have more station rather than longer deployment. This is my answer. However, if you can have a longer footprint on the ice, you can do other things. You can put a GPS there, monitor the movement of the ice surface, benchmark with satellite missions, right? There is a polar hole from IceSat 2. If you put a long-running station there, it also serve NASA's mission. So that can also be a selling point. So if I'm a business manager, I'm trying to look at which one will benefit me. I would say longer duration of the footprint can sell it better. But as a scientist, I want both. And I hope my students can benefit from longer and more stations.
Well, thanks again, Weisen. So Megan will be coordinating lunch. I think it's meeting in the lobby at noon, and then right after this. But yeah, that's all. Thank Weisen again.
Thank you.